Okay, I got handouts here. So this is our last day of notes. I'm just going to cram as much review as I can. Just even during the help session, I think this morning it kind of reminded me of some things that I want to make sure that I bring up to you. Um, so I think I'm going to skip going through the FRQs. Hopefully, we've done enough FRQs where you can kind of work through them at your own pace and practice them. And I do have videos from previous years for 2016, 2017. Um, but I just want to encourage you guys that if you're stuck on a problem and you don't know how to do it, take a picture of it, um, send me a screenshot of it, and I'll try to explain further, working the problem out in a different way and send it back to you. So I really want you to feel like you're as prepared as you can going into Monday. So and I will have a help session this Sunday, going over a last minute set of FRQs, which I will make available at the end if you want to pick up. So this is what I want to start off with. Um, Oh, by the way, I gave back your multiple choice test. Um, it's already in the grade book with the homework grades added in out of 100. So I will make these solutions available on my website. So everything is under Sunday. So under Sunday, you're going to see the link to the worksheets that I have available at the end of class, plus links to the keys for the test that you just took. So there's different versions out there. You have to kind of click through and scroll through and find your version if you want to see the worked out solutions. If you don't understand why you missed a problem, I want to make sure you guys know how to find it. So I'll send out a reminder today or tomorrow to let you know where to look. Okay, but um, grading those tests, I think I was able to kind of identify some areas where I see students missing some problems. So this worksheet is just a way for me to kind of tie up some loose ends, especially problems that we haven't seen in a while. I want to make sure that we are clear on the procedures. So I think our tendency now is when we see an integral problem and it looks messy, I think our natural tendency is we want to go to use substitution, right? And that is correct, I would say 70% of the time, but not all the time. Okay. So, but if you look at number one, this, you can tell the degree is higher in the denominator. There's more than one term in the denominator. This is a use substitution problem, right? And what's the U value here for number one? The denominator, right? Okay, so we let the denominator take on the entire U value, du dx equals 14x, solve for dx. We want the x's to go away in the numerator, and it does. We're pretty comfortable with this process. With 1 over u du, it's natural log. So it ends up, being something that this is what we typically expect out of use substitution problems, right? Pretty straightforward. And the whole purpose of use substitution is so that you can transform a messy problem into something that is more recognizable in terms of identifying what people are going to use. Right. Number two, messy problem, degree is higher in the denominator. This is also a use substitution problem. What's the U value here? That 3x cubed minus 4 inside that cube root, right? Okay, but we want to make sure you rewrite it as a parentheses to the 1/3. My bad. And then you find your u value, you find your dx. Your goal is to get that x squared to go away, and that derivative makes it a favorable match. Right, and everything is comfortable here. Everything is pretty familiar. Careful though, this is not natural log. U to the 1/5. We got to bring that up to the top and go through power rule, right? So I think this is what we expect out of integral problems, right? Just a very easy, natural process that we've grown accustomed to. But not every problem that you see with numerator and denominator, and not every messy problem you see with a fractional component is U substitution. Okay, and I want to point those out to you now. Now, if you look at number 3 here, a lot of this showed up on some versions of the quiz, and you see this looks a little messy. The tendency is, okay, you want to try to go through U substitution, but look at the denominator here. How many terms are there in the denominator? 1. So here there is no need for U substitution. Also, U substitution is not going to work because it's not the method for it. If there's only one term in the denominator, what can we do with this fraction? Split up. We can just go ahead and split up into 3 individually smaller problems and then just treat it like 3 small problems. So we couldn't do that with number 1 and 2 because there's multiple terms. And also here, well, this is 1 term, but there's 2 messy in the denominator. You see how this is a monomial here. So 1 term, you don't do U substitution, you're going to split up and rely on individual rules to handle each of them. Okay, it's not 1 big problem anymore. It's now 3 smaller problems. And then once you split up into individual fractions, clean up as much as you can. Any variable, bring them to the top unless it's x to the 1st power, then you leave at the bottom. So once you clean up all the way, you're going to see, okay, 1st term is power rule, 2nd term is natural log, 3rd term is power rule. So just be careful. If there's only 1 term at the bottom, no U substitution. Split up and handle accordingly. Okay, number 4. Number 4 also looks messy. Your tendency is you want to try to go to U substitution. It feels like the easy way to make sense of this. But again, look at the denominator there, only 1 term. Split up, it may be a U substitution, but not initially, because this is not 1 problem. This is 2 problems. So go ahead and split them up into individual problems. Clean up individually, and then decide, okay, how am I going to handle them separately? We don't have to treat this like 1 problem, like above. Right. Above, we had to go through U substitution because we couldn't split up that messy problem into smaller parts. But if you can split the problem into smaller parts, then you got to do that first before any consideration with U substitution is involved. So once you split up into individual terms, then you realize, okay, I can clean this up. I can cancel a bunch of the e's with the exponents out. 4x minus 3x is 1x. 2x minus 3x. Well, here it ends up being 1 over e to the x, but we do have to bring this up to the numerator because we do have a rule for e to the u, but we don't have a rule for e to the u in the denominator. So we got to bring it up e to the negative x. So there is a little bit of U substitution here, that negative x will produce -1, which will change the sign in front. But integral of 2/3 e to the x is handled differently than the integral of e to the negative x. Okay, the rule for e to the u is e to the u, no change. So I saw enough students miss this type of problem on the quiz that I felt like I think it's good to point that out in case you see it on the exam. Okay, you guys have the key attached. Just want to make sure that you guys use that. Okay, let me look at number 5 with you. Now, look at number 5 here. 2x squared plus minus 1 over x plus 2. Okay, so here we're back to multiple terms of the denominator. I can't split up. Maybe you're thinking use substitution, but what's the issue with use substitution? Yeah, the bottom is too low. And if I let the numerator be the u value, it's not gonna, I'm not able to get that x plus 2 to cancel out. So, anyone know what this is here? We haven't done this in a while. This is either long division or synthetic division here. Okay, so we do this if there's multiple terms in the bottom and the degrees are matching between top and bottom, or the top is higher. But typically, I don't see a lot of long division on the AP exam, so I'm just going to ignore that process. We have to go through long division of those x squared in the bottom, right? Anything higher than the linear, we can't do synthetic division. But I just haven't seen a long division problem in such a long time. I'm just going to assume that the most you're going to see is synthetic division. Okay, so I want to practice that process here. It's faster, it's easier than long division, but it's also more gimmicky. You gotta just know a bunch of rules to go through it. First thing is solve for x. Okay, put -2 outside a half box, and then place the coefficients on the first row. So I got a placeholder for x squared, which is 2. What comes next? 0, because I need a placeholder for x. There is a jump in degree. Okay. And then the -1 is for the constant. First thing you do is bring the first number down below the line. Don't change anything about it. Next up, multiply. -2 times 2 is -4. Add. Multiply again. Add. Now, another thing we got to keep in mind is we're starting with x squared, but you're dividing by x, so what are you going to be left with? Your first term is now going to be what? X. So you got to make sure you drop your degree by 1, right? So all these little tricks, you got to just remember all these little steps. You got to make sure you remember. Now, once you have this established, then everything is going to fall by 1 degree. This is linear. This is constant. And what do we call this? This is a remainder. So you got to put your original denominator under to indicate that you can't divide it all the way through. Now, is this our answer? No. Okay. So the whole point is to get to the place where you can actually take the antiderivative. So we haven't done anything calculus related yet. We just created potentially an easier problem for us to approach with integral rules. So now, usually with synthetic or long division, your first few terms are easy. your first few terms are just powerful, and the last term is a little bit of u substitution, but it's going to be a natural log. So if you want to split up into individual problems, you can, or you can just handle them as you know how. So your u value is x plus 2, ends up being 1 over u du, 7 natural log acid value of u. Twos cancel out. So okay, are we okay with number 5? Now look at number 6 here. Notice here. U substitution is not going to work. Definitely not going to be a synthetic long division. That's only going to work if my degree is higher or at least the same as my denominator. Okay. But here, what I want you to see is there is a gap. You see how this is degree 2? What's the degree of the numerator? 0. There's a gap. There's a gap of 2 or more. And that's an indication that our trig is the best way to handle it. Now, we haven't reviewed R trig in a while, but if you see R trig on the AP exam, chances are it's going to be R tangent. Okay. So I want to go through, I want to kind of hit the types of problems with the highest probability if it shows up. So this is so, and if you're gonna memorize one R trig rule, this is the one to memorize. So we need to create a situation where I have a squared and u squared separated, but my trinomial is not quite set up for that. So we have to go through another procedure. Remember what that procedure is? Complete the square. Yeah. So complete the square. We do x squared minus 4x plus space plus 9 minus space. Okay. We're trying to find a number that will allow this trinomial to factor, but whatever we factor, we got to make sure we balance it out with the same number and we don't add anything more to that expression. So the formula that we use to fill in that space is b over 2 squared. What's my b value? 4. 4 over 2 is 2. 2 squared is 4. So 4 goes in both spaces. Factor the first 3. Multiplies to be 4, adds to be negative 4, x minus 2, x minus 2. Okay, now we need the denominator to look like parentheses squared. Now I want that 5 to be inside the parentheses without changing the value. So what do I do with that 5? Make it root 5, yeah. Because root 5 squared is the same thing as 5. But I want to have this step in front of me so I can clearly see my u value and my a value. Your a value is the constant. Your u value has the variable in it. Okay, so now we go through your substitution, make it look like this. Once you do that, then we can apply the antiderivative and bring back our original variables. everything matches with my rule. Now I can apply my rule, 1 over root 5, arctangent of x minus 2 over root 5 plus c. There's no need to rationalize your denominator. You leave your answer in that form. Okay, so I want to quickly distinguish between U substitution, power rule, expansion, synthetic division, and arc trig. Again, if your degree is higher in the denominator and multiple terms in the denominator, chances are that's U substitution. If there's only one term in the denominator, it doesn't matter what the degree is, split up. It's not a U substitution to begin with. You got to split it into individual problems, split it into multiple fractions. If your degree is either the same or higher in the numerator, then you go through synthetic division. And chances are it'll be a linear, so that you can just go through synthetic and not long division. And then if there's a jump in degree, denominator has a degree 2 or more than the numerator, then it's going to be arc trig. And hopefully, if you see arc trig, it's just arctangent. Okay, a couple of other reminders that I want to go through with you. These are smaller items, but I felt like, it's quick enough for me to go through with you. So in case it shows up, it'll be good to just knock it out. So this one here, if y equals natural log of x over square root of x squared plus 1, then dy dx equals, you got to find the derivative. And I think the tendency is you look at this and say, okay, I got to do u prime over u because that's my natural log rule. But you could, but this is a really messy u value. Right? So whenever you see a natural log problem, consider expanding it before finding the derivative, even though ultimately you are finding the derivative. Right? But if you expand it, you're going to make your process a lot easier. And also, if you find the derivative here, your u prime is going to be a whole ordeal going through quotient and chain rule, and it's going to be such a mess that it'll be hard for you to match with the answer choice anyways. Right. So think about log expansion here. So which property can we use here? Natural log of a over b can be expanded into what? Yeah, natural log of a minus natural log of b. So I think that's a reminder that I want to give you in case you see a log expansion problem. Right. Same thing, if you see an implicit problem, let's say if it was like natural log of xy plus y squared is equal to 4x, they ask you to find dy dx. Rather than having to go through product implicit in here, go ahead and split this up into what first? Natural log of x plus natural log of y, right? Expand logs as far as you can before you jump into the whole derivative process. I just want to give an example. This is not the problem that we're working on, but I just thought of that. Okay, but let's do this one here. Okay, if you expand all the way out, you're going to find your derivative process for u prime over u is going to be a lot easier, a lot cleaner. Right. Okay, so natural log of a minus natural log of b. Clean this up even further, right? Rewrite that square root as to the 1/2. Bring that 1/2 down in front, and you can further avoid messy chain rules. Because once that coefficient out is in front, it's a lot easier to work with this u than this whole mess of a u. Okay, u prime over u for both. Clean up. In this case, your answer choices has common denominator. So I found the common denominator and I merged it to match answer choice B.
Number 8, I really want to show number 8 just to compare with number 9. Number 9 is really the big thing I want to hit. But number 8, I think it's also a good reminder, even though this is a less common rule. But I think it's also good to know this looks a lot like e to the u, but it's a constant raised to variable. This is an exponential function base a. So the rule for this, a lot like e to the u, but there's a conversion that has to happen. So it's natural log of a, then this the original function, and then it's the exponent's derivative. Okay, so natural log of 2 comes first. 2 to the x, 2 to the u, times u prime. Okay, I don't see it anywhere, so it's none of the options. But I want us to make sure that this is not confused with number 9. So number 9, we can't use the rule a to the u because number 9, the function is x raised to the natural log of x. Okay, so we can't say natural log of x times x to the natural log of x times 1 over x. It's not the same thing. Right. Now, what I want us to understand is that this is not an exponential in the sense that it's base raised to the exponent, raised to a variable. This is a variable raised to the variable. And I want us to recognize that this is not a rule that we have. We don't have a rule for a variable raised to a variable, but we have a way to work around it. And the way we work around it is this process called law of differentiation. So if you see law of differentiation, the chances is not that high, but I figured if it only takes me 3 minutes to go through it, I want to just spend time to go through it. So the idea is that I don't have a rule that can handle a variable raised to a variable. But if I can bring that exponent down at the base level, then maybe I have some more options available to me. Well, what can I do to bring the exponent down? What if I can make it part of a natural log expression? Then the exponent can be free to come down because I have that log property. So if you see a variable raised to a variable, the workaround is taking the natural log of both sides, because that opens up the property to allow that exponent to come down. Okay, so let's try that. Natural log of y is equal to natural log of x to the natural log of x. So now that we're sitting in a natural log expression, this exponent can be free to come down, and it's not a derivative process. This is a log process. But when that comes down, we have more options available from a derivative standpoint. So if I want to find the derivative from this stage, it's a lot easier. What becomes of this left side? Natural log of y becomes y. 1 over y u I dx. Good. So u prime for u, but implicit because y is not by itself. And this side, we got to go through what? 2 terms here. Product rule, f prime g plus f g prime. Clean up as much as you can, f prime g plus f g prime. Then at the end, make sure you bring your y over to the right side. So dividing by 1 over y is same thing as multiplying by the reciprocal. And then once you get that y dy dx by itself, you bring the y back in terms of your original variable x, or original equation. Okay, I want to highlight a few problems from packet 6. So if you have packet 6 on you, If you don't, just follow along then. There are a couple of kind of strange setups in terms of problems that I want to point out. I didn't really go through them in class, but I figured we'll use this time to go through. So page 63 in packet 6. Right. You're given a function. It says this function is the solution to which of the following differential equations. So we're trying to figure out which of these match with this, which of these match with this equation. You have a lot of mention of y double prime and y prime. So how do we match it up? So the first thing you do is go ahead and find y prime and y double prime, right? We want to be able to, we basically want to find a representation for y prime, y double prime, make some substitutions and actually test these to see which one is actually going to get to the answer that we're staring in front of us. So we don't know what y prime, y double prime is, but we can find it, right? So let's go through our derivative rules and find y prime, y double prime, and it's going to feel like a little bit of a puzzle to try to see which one is going to work. Okay, so e to the u is e to the u times u prime. Five x becomes 5, and 7 goes away. Okay, so there's my y prime. Let's find y double prime because there's a mention of y double prime in each of these answer choices. What's y double prime? 3e to 3x times 3. So which of these can I insert and replace and make my way to this solution? So the way that we can test this out is we're just going to test these. Sorry, we're not going to use this function anymore because we already have y prime and y double prime, and then the solutions is not calling for y prime, y double prime. We just had to be able to plug in and make it a true statement. It's just got to come out to equal to 0. So we just test each of these here. If I plug 9 in here, I get 90 to 3x minus 90 to 3x plus 15 minus 15. This ends up being 0. This actually ends up being the correct answer. If I test the other ones, it's not going to quite work because 90 to 3x minus 90 to 3x, that cancels out. But then I get plus 15 plus 15, that's 30. So it's not quite equal to 0. Okay. This doesn't work either because I'm not able to get the coefficients to match up and cancel out. Okay, so I just want to kind of show you this specific type of problem. These are verifying problems here. Let me just kind of walk through page 65. Number 5 is the same way here. It says that the following, which are solutions to the differential equation. So there's y double prime, y prime, and y. So this is a little bit longer because you have to find y double prime and y prime for each of these. and then use testing them out to see which one will actually plug into here and actually get you a 0. And the second and third one does work itself out, where if you plug all these y double prime, y prime, and y with this specific function, it does end up working, but the first one doesn't work. So have you guys work through that on your own? I want to just point out the steps here. Here, you're just going to find each of the derivatives, make the substitution, and see if it works. If it works, then great. You know it's a differential equation for the solution for the equation. But if it doesn't work, then you got to move on. Okay. Let's see. I did a help session this morning, starting on page 53, and I just I thought of a few things just want to point out. So on page 53, if you see a differential equation problem that's a multiple choice, understand that it's a bit of a longer problem. So I'm kind of conflicted about, is it worth the time spending, all this time on the multiple choice question? Even if you know how to do it, it just takes so long that, is it coming at the cost of being able to see easier problems down the road, in the multiple choice section? So it's almost like you almost want to, if you know how to do it, great, circle it, come back to it when you have more, when you've already made sure that you have enough time at the end. Because you do want to manage your 60 minutes very efficiently, because you do have to work through 30 problems. And you would rather, seek out easier problems than having to spend 5 minutes on a problem like this. Another thing I thought of was this. Here's an easy way, like a cheat way to eliminate wrong choices. You see this initial condition order pair here? It's got to work with the solution. So if you can plug in an order pair, and if you know it doesn't work, you eliminate those wrong choices. So that's a quick way to cheat your way through a problem. It may not get you to the right answer, but it can eliminate the wrong ones. Okay. So it doesn't work for every one of them, but that's just if you're down to 2 choices and you have absolutely no idea how to select your answer choice, and do the easy thing, plug in the order pair. And also that also works if you're doing a free response question and you are at your final answer and you're just not, you want to get extra assurance that you're at the right answer, plug in your order pair. Your order pair has to work. If I plug in 1 into my expression, I got to get a 4 in return, right? If I can plug 1 and get a 4 in return, it's not a foolproof way, but it does help give you some extra assurance that you're on the right track, that you've at least created an equation that works with the order pair. Okay, another thing I want to point out, I think I mentioned before in classes, is that don't let here, I'll talk number 5 first. When you see a trig function with an exponent, like between the tangent and the expression, know that this is a shorthand way of writing that entire expression as being raised to that power. So I would spend the time to rewrite it, because if you rewrite it with a bracket, it's the same thing, but you're less prone to making a mistake in this form than this form. It's harder to see the chain rule component as it is to have a bracket outside. So this is on page 56. If you see that bracket outside, you can clearly see, okay, chain rule, outside derivative, bracket, 2 bracket to the first power, then tangent derivative, tangent is secant squared of u, and then times u prime times 6x. Right? But without that bracket there, it's easier to make a mistake because you don't see all the parts as clearly. And then problems like 8, 9, and 10, especially 9, I do want to point out that I think we get a little nervous when we see a letter that we are not accustomed to, like an A or B or a K. It's like, what do we do with that K? You know, that's gonna throw us, you know, throw our steps off. So if you are nervous about seeing a constant that they gave you, then just put a number there instead and treat it like as if that's just a number, right? I know it's easier to see a number there, so treat it like you would with a number. And, you know, you can still get to the answer here, find the fifth derivative. Pretend like, you know, how would you approach this problem with e to the 3x? It'll be e to the 3x times 3. And if you keep finding the derivative, another 3 will pop up. So if you get nervous with seeing a constant, replace it with a number, and then treat it like you would with it as a number, and then you can bring back that constant. Okay. I think so many times we treat a constant like a variable, and it just throws off our answer. So if you ever see like a constant like a K or A or B, if it helps, put a number in place of it, and then that way you can treat it like that number, and you can bring it back to get to your answer. Yeah, so hopefully you guys will have a chance to work through all the FRQ packets and your and the multiple choice packet. Couple of things that I think would be good to do on Sunday is look through your formula sheet. So this is on page 69 and 70 of your packet 6. I think I put it in both packets, right? Make sure you are comfortable with all the big items. Memorize the most important derivative and integral rules. But if you want to do more than that, then you have that exam detail packet that I gave out. And it has the full set of derivative and integral rules, all organized with the key. So different versions of it. So hopefully you'll get a chance to practice that. Okay, and then finally, I have some additional packets if you want to. Now, I think some students who were here yesterday, they can pick them up already. These are not mandatory, but I just want to talk about what they are. So I have packet 7, which is miscellaneous topics. I think this is the lowest priority. It's just minor topics that may show up on the exam. Packet 8 is a set of FRQs that you haven't seen yet. These are from recent alternate versions of AP exams that College Board created. I put them, I made a packet with 8 FRQs along with the key. So you can pick it up. We'll go through the packet on Sunday on Teams. I'll send you guys a link. And then I have another handout with some last minute reminders that I found on the website. And then also unit circles. So just keep reminding you that unit circle is fair game. So if you see an integral problem like this, or like this, you have to be able to work it out by hand, right? So sine becomes negative cosine. Right, and then you evaluate. Okay, normally I would say you can leave your answer unsimplified except for trig. You got to make your way down. So you have to know that, oh, this is negative √2/2. This is 0. And then this is your answer. Okay, so you cannot leave your answer in this form. You got to make it one step further. So I want to make sure that you guys are comfortable with unit circle values, and then you keep those
you have those memorized. Okay. If I think of any other last minute reminders, I'll send you guys through text. But yeah, come up and you come get your phones. And then if you want to pick up those packages, you can, but they're not for grade. You have to pick them up. Okay. Right. It goes. Oh, it does. Yeah. Thanks.
Extra one of the, thank you.
Can I just, check? You did, okay, okay, I see, I'm fine, I'll just, mark you off. No, that's it, yeah, that's it, thank you. No, we have everything, we got packets 5 and 6 and this, that's all.
All right, okay.
I got you checked, Corbin. I got you checked off for packet 5, okay.
This.